Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 5th, 2025, which was about 6 days ago. The standout idea is a framework that reliably estimates real robot performance using a small number of hardware trials, plus many simulations, delivering confidence intervals while cutting hardware effort by 20 to 25%. The paper is titled, Reliable and Scalable Robot Policy Evaluation with Imperfect Simulators. And as we'll see later, the implications for trustworthy evaluation are quite significant. The approach uses prediction-powered inference with betting-based mean estimation, works best when real and simulated outcomes correlate, and remains conservative when they do not. Alright, the previous segment framed the goal and the prediction-powered approach. Figure 1 lays out the SureSim workflow that blends small, real trials with many simulations to produce a confidence interval on true mean performance. The top left panel shows small-scale real evaluations. The bottom left panel depicts large-scale simulation runs whose mean is cheap to estimate. The middle panels use paired real-to-sim evaluations to correct simulator bias, and the right panel summarizes the final confidence guarantee across the task and environment distribution. Well, Figure 1 sketched the workflow for combining real and simulated trials. Figure 2 shows a diverse set of about 120 tabletop objects used for real evaluations, which include many toy kitchen items and common household shapes. The collection approximates the target distribution of objects, so policy performance reflects variety in size, geometry, and texture. These objects also support paired simulation by providing reference dimensions and poses. Okay, the previous figure summarized the real object set. Figure 5 reports hardware trials saved versus a real-only baseline, with bar charts for a diffusion policy on the left and for pi0 under moderate correlation on the right. SureSim and SureSim UB save roughly 20 to 25%, which matches the overall claim that simulation can replace many hardware runs. The two-stage variants save little and sometimes go negative, indicating inefficiency. Error bars show the standard error across 100 random draws. So the previous figure quantified hardware savings. Figure 4 shows how confidence interval width shrinks as additional simulations grow for a diffusion policy with 60 paired trials. The orange SureSim and gold SureSim UB curves drop toward the dotted rectifier line, which acts as a lower bound set by real-to-sim mismatch. At 700 simulations, SureSim reaches about 0.16, roughly a 14% reduction versus the classical 0.187. The two-stage variants remain noticeably wider. So the previous figure highlighted diffusion policy gains with added simulations. Figure 6 shows interval width versus additional simulations for pi0 under moderate real-to-sim correlation with 60 paired trials. The orange SureSim and gold SureSim UB curves drop toward the dotted rectifier limit and level off by about 500 simulations, while classical stays flat. The purple two-stage methods shrink more slowly. The right inset presents representative confidence intervals, which place SureSim clearly tighter than classical. So the previous figure showed shrinking intervals under moderate correlation. Table 1 summarizes the setups and key statistics, which include paired counts, added simulations, correlations, and sample variances. The correlation spans strong at about 0.97, moderate near 0.70 and 0.59, and effectively 0 at minus 0.05. The rectifier variance was below the real variance in the moderate and high cases, so simulation helped tighten intervals. In the low case, the rectifier variance was not smaller, so added simulation offered no benefit. Two takeaways stand out. Prediction-powered inference with betting-based mean estimation gives finite sample valid confidence intervals, and when simulation correlates with reality, it trims hardware trials by roughly 20 to 25% while staying conservative when correlation is weak. The broader impact is scalable, trustworthy robot evaluation that informs deployment and drives better simulators. That is it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.